All right. Good morning, folks. Happy Wednesday. This is actually the last Wednesday we're technically meeting for Math116. Next Wednesday, you have your exam 4, and then that'll be it for the class of 116. And then the next time we meet on a Monday or on a Wednesday, you all will be in Math 104. Okay? So we are going to go ahead and get started this morning. I'm going to give people maybe another 60 seconds or so to trickle in. We are going to start this morning with 9.3. Okay, we're going to start this morning with 9.3. And the goal today is to do 9.3 as well as 9.4. Okay. Now 9.3 is basically going to be an extension of our 9.1. So in 9.1, we only looked at systems where we had linear equations. So 2 lines, that's it. And now what we're taking a look at in 9.3 is what happens when we have lines that intersect a circle, or lines that intersect a parabola, or lines that intersect an ellipse, and kind of thinking about what that looks like, okay? And so what we're going to do to get things started, I think enough folks are here. We are going to do a little bit of, let's kind of see what we remember kind of situation. All right. So I'm going to put you folks into some breakout rooms. We're going to take a look at the launch. And let me just share my screen for that first so we know what we're talking about. Okay. So this is 9.3, and there's 2 questions here, okay? I'm gonna give you folks about 10 minutes in your breakout rooms, again, mostly to just kind of play around with those, think about some strategies. And the key here is I really want us to start to think, how can we bring equations in to model those situations, okay? So you can talk about it sort of logically with your group, but at the end of the day, what we're really looking for is like, how do we kind of construct equations to go with these word problems, okay? Are there any clarifying questions before I whisk you all away? All right, well, let me set those up real quick. Helpful to have more or less people in the rooms? More, okay, cool. All right, don't forget you have that whiteboard feature that you can write on the screen. Even if you don't have a tablet, you could just use your mouse. It's not quite as nice, I think. It can be a little clunky, but it is a nice way to kind of visualize the work that you're trying to talk about, okay? All right, so you folks are in 4 breakout rooms, and I will see you back here in 10 minutes. All right, folks. I think we've mostly made it back. I heard there were some weird things happening today in the transition to the breakout room, so I apologize for that. Hopefully you had somebody else in that cyber room with you. Okay, so the purpose of these problems is a few things, okay? I know that for some of us, word problems are traditionally something that we just do not like, okay? And that may be the case, but at the same time, as we move forward in math, it's gonna be important for us to really be able to take an equation or take words and translate them to an equation, okay? All right, cool. So I know that probably was not enough time to solve both problems, or maybe not even one, but I did want to talk about the process real quick, all right, and just kind of highlight a few things. So when I'm looking at problem number 1, as soon as I read the first sentence, I stopped and I wrote an equation that went with it, okay? So the two numbers that add up to 300 is highlighted in the green, and then the equation below that's highlighted in the green is the one that goes with that, okay? Same thing with the pink. One number is twice the square of the other number, okay? And just a couple things to remember, that is that equal sign, all right? And we need to be really careful about our language here, because this does not say square root, it says square. So we want to make sure we have a power of 2, not a square root. And so in this case, even though there's a square, I think that this should be the kind of question that we're like, oh, we should use substitution. Because they're telling us x equals this, so everywhere you see an x, you should put in 2y squared, okay? And so that's where I did the little note that said substitution. And after I substituted, I got this line, 2y squared plus y equals 300, okay? So I would say that's sort of like the first half of the problem. Like, you set up the equations and you use both equations to create one equation. Now, at this point, it's going to be a variety of skills that you've learned in the past, okay? Primarily, I picked this question because this is a situation where you have to know how to factor, okay? And so all of this, as soon as you see the square, your mental cue should be move everything to one side, set it equal to 0, okay? We want that pathway in our brains to be super, super strong. We see the quadratic, our first thought is move everything to one side, set it equal to 0, okay? And then we need to be able to factor. We need to be able to determine whether we can factor or whether we can't. And if we can factor, we should be able to do that, okay? So you factor, you set them each equal to 0, and you actually get 2 sets of answers. So one potential solution is that y equals 12 and x equals 288, okay? But another possible solution is this one here, where you have y equals negative 25 over 2 and x equals 312.5, all right? Now, this question intentionally does not say only the integers. It doesn't say only the integers. It says any numbers. What are those numbers? Okay. And when we look at our answers, we probably could have guessed and checked the one in the box, but it would probably be a really long time of guessing and checking before we got the one in the bubble. Okay. Now, these are considered nonlinear equations because this one right here, this one is linear, okay? X plus y equals 300. But this one is non-linear. All right? Because I have the square. I know that the equation in pink is like a sideways parabola. And because I'm looking at a line in the green and a sideways parabola in the pink, let's kind of put some pictures with this. So if I have a line, and again, I'm not really sure which direction it goes necessarily, but let's say that the green line looks like this, and the pink parabola, oops, wrong way, that one opens this way. From that picture, how many solutions should we have? Yeah, we should have 2, exactly. And we have 2 because we have this point where the green and the pink cross, and we have this point where the green and the pink cross, okay? And that matches up with our answers because we have 2 sets of answers, which is good because we have 2 sets of points that they cross at, okay? So the nonlinear part really means all that work we did with factoring and completing the square, we really got to make sure we still know how to do those things, even though this is a totally different unit. Okay, the idea of when should you factor versus when should you not is not something that goes away. Okay, so that was question number 1. If you have any questions about sort of the nitty-gritty details here, please feel free to email me about that. Yeah, Ethan, what's your question on number 1?
I was just gonna say, so our thinking was we saw one number is twice the square of the other number, so we came up with x plus 2x squared equals 300. And then we said y plus square root of y over 2 equals 300 as well. And then we tried to solve it that way. Would that still have worked?
I mean, it would. I bet it would have taken you a lot longer.
Yeah, it was taking really long.
Yeah.
But I just wanted to see if the, you know, the logic behind it worked.
For sure, for sure. Yeah. A lot of times we actually, for those of us who feel really good about writing equations, sometimes we almost skip that step of writing 2 separate equations. Sometimes we're able to jump right to something like this, right? Which is pretty much what you said. That's totally fine. But I do want us to understand that it ties back to this idea that we're essentially saying, like, we have a parabola and we have a line. How many times do they cross? All right, let's take a quick look at number 2 over here. Okay, so bringing back a little bit of that idea of cost and revenue that we very briefly touched upon the other day. Okay, so we've got a cost function, we have a revenue function. Now, if they want to make a profit, that means that they should actually have the difference of those two, like the cost and the revenue, should be at least equal to each other. It could be more than that, but they have to be at least equal to each other, okay? And so that's where I got these two, this first equation from. I said that the cost has to equal the revenue, okay? That's sort of the first step for this question. Knowing that, like, when cost equals revenue, that means that after that point, you're going to start to make a profit. And so I use the same strategy that I saw from part 1, which is I see the quadratic. My immediate thought is move everything to one side, set it equal to 0. And so that's how I got the next line, 5x squared minus 110x plus 150. Now, one of the tricks I want to remind us about as we move forward is being in higher level math does not necessarily mean being able to work with bigger numbers, and that's what makes you better at math. I think in contrast, the higher up we move in math, the more we want to think about being clever. And so what I did between the second line and the third line is I divided by 5. I wanted to make my numbers smaller, right? If I have to factor or if I have to use quadratic equation, I would really rather not work with larger numbers, okay? So this is kind of a good strategy to think about. Be on the lookout for a greatest common factor, okay? That idea of dividing away that greatest common factor can actually save you a little bit of time, maybe even help you be a little bit more accurate in the work that you do. Okay? Now, this one is not factorable. And so we really want to make sure we also remember the quadratic formula. And I'm sure that if you're having trouble remembering that quadratic formula, Richard would be happy to sing it for you anytime you want. But when we plug all those numbers into the quadratic formula, we get 2 answers out, all right? We get x equals 1.42461 and x equals 20.539. But let's take a look back at our green equation and our pink equation again. What shape is our green equation?
It's a parabola.
It is a parabola. Is it facing up or down or left or right?
Up.
It is facing up, yeah. So this is our cost function. What shape is our revenue function, the pink one? Yeah, it's facing down, and it also happens to be a parabola. So check this out. According to our picture, we should have 1, 2 solutions, which matches because our answers, we found 1, 2 solutions. Okay. So it turns out that if a company makes, they're not going to make 1.461 laptops necessarily, but we're rounding to the nearest number. So if they make between 2 and 20 laptops, then they're going to be making a profit. Okay. Sometimes the more you make doesn't necessarily mean that you're going to be able to sell all of those, right? Maybe they could make 500 laptops in a day, but if they only sell 20, then they just actually spent all this extra money making laptops that they can't sell. Okay. And so that's why there is this idea of a range of profit. We really want to hit that sweet spot about how much money we're putting into it, but also how much money we're getting out of a situation. Okay. So again, I know this was a quick look at some word problems. Again, the point here is I really want us to start to realize if we're scared of word problems, to know it's not going to go away, and that there's plenty of time between now and when it might come up again to really get this under our belts. Okay. All right. So that being said, let's go back and take a look at some pictures, okay? So we're gonna take a look at some types of nonlinear systems of equations. And first up, we're gonna take a look at a parabola and a line. So I feel like, I don't know if folks can draw on here, but if I were to draw a parabola and a line, we saw earlier that we could draw a parabola and a line, and it could cross 1, 2 times. Okay. My question to you is, how can I modify this so that I only have one intersection? Yeah, if you can annotate, go ahead. I'm not sure if I have the settings that way, but that would be cool. Cool. All right, we got one parabola. Yes, exactly. This is really cool. I'm actually excited about this. Okay, yes, and Thea had a great idea. She said make it a vertical line, exactly. Ethan said make it tangent to the vertex, could be at the vertex as well. It could actually be tangent anywhere on the parabola, okay? Now, I'm going to draw one as well because the one thing I realized is that I don't think those pictures will save on the notes, which is sort of a downside, but I think it's cool for you to put those ideas out there as well. Okay, so one solution. All right, so I think you had a parabola like this. You could have like a line like that, okay? And presto bingo, we've got a situation where we have one solution, okay? What about zero solutions? How can we draw a situation where we have no solutions between a parabola and a line? Okay. So yes, exactly. I'm so glad that someone drew that diagram. So we've got a parabola facing up and a line. And if we were to extend, like put arrows on the ends of the parabola, it keeps going up forever and ever. Exactly. It's never going to intersect that line below. Perfect. Okay. I've had students in the past, let me just copy down what you have right now. So you had a parabola and the line. That's totally valid. Okay. I've had some students who did this though. They were like, oh, this parabola and this line are never going to intersect. And sometimes to make their point, they'd like draw the parabola like really small. They're like, well, it's just a really small parabola. But I think we know that last situation doesn't really work because the arrows are there, whether we draw them or not. So at some point, that sideways parabola will cross that line. So we really want to think about that line more like a directrix, right? It's sort of on the outside of the parabola. That guarantees your parabola and your line will never intersect. Cool. Press and hold. Oh, really? I thought you could only do that with circles. That's so cool. Is that how some of you have been drawing such perfect parabolas on your homework? Cool, cool. I love this. All right, so what I'm gonna do is this. We're gonna repeat this process with a circle and a line, okay? So I want you to think about like how many solutions you could have with circles and lines. So one circle and one line, how many different ways can you find solutions? And then I'd like you to think about the circle and the ellipse. How many different ways can you think about solutions between a circle and an ellipse? Okay. And the way I'd like you to think about them is going back to the picture. So can you draw a circle? Can you draw a line? And make it so that they cross a certain number of times. And think about how many cases you can come up with, okay? So let's do this. Shall we try the breakout rooms again and hope that nobody gets lost in cyberspace? I think these could be some fun conversations. Let's try this. All right, let's do maybe about like 7 minutes to draw some pictures. If you get lost in cyberspace, I think you can still draw pictures by yourself. I'm really sorry, it's not intentional. But let's give this another try. There we go. Okay. So for the circle and the line, I hope you all got solutions that kind of look something like this, yeah? That we could have a line that crosses a circle in two places. We could have a line that crosses a circle in one place. And we could have a line that never crosses the circle, right? So two solutions, one solution, no solution. All right. How about the circle and the ellipse? I set it up this way just to kind of like do it in a methodical way to make sure I wouldn't miss anything. And the only thing I put down so far is the 0 solutions. But is there anyone who can can more than one of you draw in here at the same time?
I think we should be able to. It's like where it says you are viewing Judy Wu's screen, and then it says view options, and then I just pressed annotate.
Oh, cool. Well, give it a go. Let's take a couple moments and see what folks came up with any of these diagrams. What'd you get for 4 solutions or 3 solutions? Could you draw a picture where the circle and ellipse cross only twice or only once? Folks, these are so good. This makes me so happy. I really like this part of the lesson, and I was nervous about how it was going to go online because I like to have folks come up and like draw things on the board, but I didn't really realize that we could do that. Yeah, how are you folks who are drawing like with the very, very perfect shapes? How are you doing that?
On the draw section, they let you choose like your the size of the brush, or you can do arrows, or you can have a rectangle or a circle, and
Oh, cool. Well, this seems like a good tool also for if you folks are studying together in like a Zoom room or something like that, just to kind of think about all the ways we can. It does kind of look like a solar system, right? That 3 solutions one, I was like, oh, it kind of looks like which planet is it that has like the rings? Saturn? Saturn has rings. Jupiter has rings. No, Jupiter has moons. I don't know. Things I should know for trivia, right? Oh, if you press shift while drawing a shape, it will make it a perfect circle or square. Okay. Ah, but it has to be in the ellipse or rectangular mode. Cool. If you haven't tried it yet, go ahead and just kind of try drawing something on the screen. School appropriate, of course, but like try some of these tools because I think, what better time than now? Aw, look at that little heart. How did folks get the little heart on there? Whoa. Yeah, let's take some time to figure that out right now. Oh, there's a stamp feature. Where do you find the stamp feature? Oh my God, there's star stamps. This is the best day of my life right now.
when you press annotate, and then it has mouse text, so I can like literally type a text or draw, and then next to it stamp.
Oh, okay. So I have sort of a toolbar at the top of my Zoom screen, and there's like the mute, the stop video, the security, whoa, the participants, and then like the second one from the end for me it says annotate. So hopefully you could see that one. If you click on the annotate, yeah, then you should see the stamp ones, the erasers, you can type, you can spotlight. So that arrow is the spotlight one. Oh, this is a sad stamp. The X. Oh, okay, so if you click on draw, they have a bunch of things for you to choose from, like the rectangle or the oval or the ellipse. Yeah, and then you could do it there. Oops. Huh. Cute. Makes me happy. All right, so let me take a moment and try and regenerate some of these one solutions so that it gets on on the saved notes. But yeah, exactly. The one solution is you have a circle and actually I wonder. Maybe they just touch at one spot like that. So that's their one solution. Yeah. For the two solutions, yeah, exactly. We're looking at some sort of, let's drag that one over. Let's drag this one over, and I can arrange them in a variety of ways, but we can kind of see that that purple one and the green one cross in two spots. Namely, they cross here and they cross here, okay? But it could also be like, let me see if I can get this. Whoop, no, no. Yeah, like that would be one solution for the red one, and then nope, nope. Right there would be one for the other solution, okay? With the three solutions, I think that is a beautiful photo or diagram. I hope I can replicate that. Whoops. Ah. Okay. Let's maybe make this a little bit longer. And maybe the trick for this one is making it so that it touches two times, like they intersect twice on one side, but then only one time on the other. Okay. All right, the four solutions I think is also a great one. So let's see if I can duplicate that. We've got an ellipse, and then we'll go back and grab the circle. Well, we're gonna make this circle a little bit bigger, right? And then we could see that it crosses 1, 2, 3, 4 times. And then, why are there so many question marks by the 5 solutions? And how come no one put anything in for 5 solutions? It's scary. What do you mean by it's scary? I don't know. Did anyone come up with any ideas on how we can make an ellipse and a circle cross 5 times? Okay, well, I'll let you folks kind of play around with that and see. I know some of you are very visual and artistic folks out there, so I don't know, kind of doodle around, see if you can come up with a circle and an ellipse that cross 5 times, okay? So maybe we have a circle and an ellipse that are exactly the same shape. Yes, then they would be the same, but that's more than 5. Okay. Well, sometimes we don't resolve everything. Sometimes we need a little, think about it, see how it goes kind of situation. All right, I like these ideas. like the 4 solutions on one, but one on the edge. Ooh, okay. Someone attempting it right now? That's, looks like 2. Okay. Well, I'll let you folks think about it, all right? We can come back to it later. Oh, we've got 2 intersections there. Ah, you can only have 1 circle and only 1 ellipse, though. One, two, three. Okay. All right, I might have to, oh, this is weird. All right, how do we get rid of all of the layers now? This is sad. I mean, I don't want to lose them, but I think we might need to. Whoa, whoa. How did folks?
Everyone just needs to clear their own work.
Oh, okay, okay. So I need to clear my annotations. Oh. Okay, cool. Oh, yeah, you can tell that I have not used this feature before. Yep, there's a save button. We can save it next time. All right, well, thanks for playing along. I know it's kind of silly, but I think, no matter, well, for a good chunk of the next few classes that you're going to be taking, there is still a lot of room for you to leverage your ability to visualize things. That if you can visualize things, that might actually make your computations like make a little bit more sense, or it'll help at least sort of give you an idea of like what it is that you're trying to find or what it is that you're trying to do. Okay. And so that's why you'll notice for all of the questions in today's section, I said solve it graphically because I want us to be able to graph. This is why we did a lot of the work with the parent functions. This is why we've done work with the conic sections even. So we're going to see some conic sections in here. But then I want us to also make sure that we're improving and growing in our algebra skills. So now we're saying, okay, I can graph it, but now we can also solve it algebraically. And why is it so important that like sometimes we remember that plus minus sign? Okay, that's actually going to be a big part of our conversation today. So let's take a look at example number 1 here. So we have, let's get some colors going here. We have this y, ooh, that's not a y, x minus y equals -1. That's one function that we're looking at. And then we have another function. I honestly spend too much time picking colors sometimes. Like, which color should we use this time? Let's go with orange. Okay. So we have y minus, oh gosh, we have x minus y equals -1. And we have y equals x squared plus 1. So tell me some things you know about those two functions. Like what shape they are maybe, or what graph transformations are happening. Okay. The first one is a line. A plus, David, that is indeed a line. All right, can you tell me a little bit more about that line? Or can someone else tell us more about that line? Or the other function, whatever. what do we know about this system? Okay, because we see an x squared, we know that the second one is a parabola. Yay. Can you tell me the direction of this parabola? Because now we know they could be up, down, or right, left. Which direction is this parabola? It's facing up, good. Okay, and let's see. David said that the line has a slope of -1/1. Let's see. Maybe it would be helpful if we isolated y. So x plus 1 equals y. I know that's usually backwards from the way we normally write it, but I could see here that the y was negative, which means if I move it to the other side, it's going to be positive. Okay, David says, how do we know which way the parabola goes again? So if it's an x squared, okay, and that was one thing on the last exam, a lot of people were like, well, it's the first one, but it's the what variable that's squared that tells us the direction. So if I have an x squared and it's positive, it will face up. But if I had like y equals -x squared plus 1, that would be like a facing down situation. And if you made it y squared, then we would be looking at parabolas that open side to side. Yeah, exactly. Okay. All right. So back to the line. Now that we've sort of rewritten it, when your y equals mx plus b form, what's the slope? What's the y-intercept here? All right, so we've got a slope of 1 and a y-intercept of 1. Okay. And for our parabola, tell me, are there any graph transformations that make this different from a regular parabola where you cross at the origin? The +1 indicates that it goes up 1. Exactly. This part right here, you know, we're used to looking at much more complicated graph transformations. I made you guys do like, it goes right or left, it reflects, you have to factor things out, and then you move it up or down. But the reason why we spent so much time working on those more involved cases is so that when we see cases like this, our reaction should be like, oh yeah, this is really easy. It's just a regular parabola, but we go up 1 unit. That's exactly what it is, okay? Now, since we're actually looking for a solution, we actually want to be more detailed in our graphing, okay? So I'm gonna plot pretty much every point that I can for the line, and I'm also going to plot all of the points for the parabola, okay? So for the line, I'm gonna start at 1. So this grid is a little funny. I'm counting every 2 boxes is 1 unit, okay? So here's my y-intercept, and from there, I need to draw a slope of 1. So up 1 over 1, up 1 over 1, up 1 over 1. And then because I want to make sure the line extends the entire graph, I'll count in the other direction as well. Whoops. And I'll go ahead and make that all connect. And there I've got my line, okay? Now I know with lines, we're used to drawing pretty accurate lines. Like most people will draw 2 points, get a ruler, connect it, and then it's pretty accurate, okay? one of the reasons, so if you've ever lost points on, like, maybe I said, I want you to plot all the points on the parabola, and you were like, well, I don't know, I just sketched one real quick, like, how come I can't just do this, is for this case precisely, which is if we randomly draw a parabola, even if it has the right vertex, we might not be able to tell from our picture what our solution is. So we need to make sure that we're fairly accurate about the points that we plot, okay? So we know that our parabola doesn't move side to side, it only moves up one. And look, our first point that we have on our parabola is already on that pink line, which means we have one solution guaranteed. There might be another one, I don't know, we kind of have to graph and see. So here's our vertex. Now, from your vertex, all right, let's think about plugging in some other points. So if I plug in 1 for x in the orange equation, what y value do I get out? Yeah, if x equals 1, what is the y value that goes with it? Oh, good, it goes to 2. Oh, shoot. We have a second intersection, which means that we already know that's going to be it. We can't have a parabola across a line more than 2 times. But for the sake of practicing our drawing, let's draw out a few more points. If I plug in -1 for x, what do I get for y? 2, okay. And some of you might have been able to find that using symmetry, okay? You know that if you get half the parabola, you can draw the other half, okay? What if we plug in 2, what do we get for y? We'll get 5. Oh, hi Arlette, good morning. All right, so 5 is off the graph. It's gonna be somewhere here. But if we connect the 5 points we have, okay, now we can see that we have 1 intersection and 2 intersections. So from here, we can tell that there are 2 solutions, okay? There are 2 solutions. So now our job is, let's do this algebraically so that and we know we should end up with 2, and we know what those coordinates actually are. So one coordinate should be 0, 1, and the other one should be 1, 2. Right? So if we want to solve a system algebraically, okay, in general, what that means is that we can use an idea of setting the 2 equations equal to each other, okay? But to kind of frame that a little bit better, if you have y equals 5 and y equals x, what does x equal? Yeah, x equals 5. And I think that makes sense for us because if y is 5, but y is also x, then x and 5 have to be the same, right? What if you had y equals 10 and y equals 5x? What does x equal? Okay, you get 2, right? Because we know that 10 must equal 5x. And then when we do a little equation solving, we get x equals 2. But what we're doing is we're saying this and this are both equal to y, so let's just set them equal to each other. Or 10 and 5x are both equal to y, so let's set them equal to each other. And so when we look at our system of equations, that's actually one thing we need to make sure we do first is, are they both equal to y? As soon as you have them both equal to y, then you can set them equal to each other, okay? So we can say that x plus 1, which is our pink line, is equal to x squared plus 1. Okay, so this is the pink line, and this is our orange parabola, and it comes from the idea, it comes from the idea that y equals y. So we're almost doing like a double substitution, okay? Even though they're different colors, the orange y is equal to the pink y. And so then we know y equals x plus 1, so we can substitute that in. And we also know that y equals x squared plus 1, so we can substitute that in on the other side. Okay? Now is the time to like go back in that toolbox and think, oh, how do I solve this question? Okay? So what are some ideas that folks have around this? Get all the x's together, okay? So let's go ahead and, which one would you like to move? You want to move the x or you want to move the x squared? I like that instinct there. Let's take this x and move it to the other side. We get 1 equals x squared minus x plus 1. Okay, even better, right? Let's move all the x's together, but as soon as we see that quadratic, again, that brain pathway that I want us to have and be so strong in, we see the x squared, we think automatically, move it all to one side and set it equal to 0 so that you can try factoring. And so that means that we'll also move that 1, so we'll get 0 equals x squared minus x, and then 1 minus 1 is 0. Okay, so we've got 0 equals x squared minus x. How do we solve this right-hand side? Like, how do we factor that? Good. We can actually use one of the ideas we saw earlier, which is look for the greatest common factor. Turns out there's an x in both terms, so 0 equals x times x minus 1. And now we can say x equals 0 and x minus 1 equals 0. Okay. Now this one I need to do a little bit of work, add that 1 to the other side. And now I have my two x values. And check this out, 0 and 0, right? One of our solutions is the x value to one of the crossing points. And 1, 1. And the other x value is the x value for the other intersection. So when we're solving these equations, like, let's keep in mind, these are intersection points. And so if I leave my answers x equals 0 and y and x equals 1, I haven't finished the problem, right? Because in order to know where two functions cross, I need to give someone very good directions. I need to give them an x value and the y value that goes with it. So how should we or could we find the y values that go with those x values? We could plug them into either equation. Great. Now, I think these numbers are pretty easy to work with, right? We've got 0, we've got 1. I think it's equally straightforward to plug the 0 into the pink equation or the orange equation, okay? Just for kicks, let's kind of do one of each. So if I plug in 0, I get y equals 0 plus 1. I get y equals 1, which is excellent because this one is the y value for that intersection point. And I could plug it into either one of the equations. So let me try plugging this into the x squared plus 1. So 1 squared plus 1, y equals 2, which is real good because this 2 matches that 2. All right. And there we have it. We have a parabola and a line. We knew that they could cross up to 2 times, but from our diagram and all our knowledge of graph transformations, we could tell that they actually crossed 2 times. And we were able to confirm that answer algebraically because we knew it's okay to get 2 x values because these 2 equations cross 2 times, okay? But once we got the x values, then we had to find the y values that went with them so we could give very good directions about where the solutions are, okay? All right, how's this feeling out there? Good, not so good? Goodish, okay, goodish. For folks that are saying goodish, or maybe the folks who are quiet, is it like we just want to see more examples that would make us feel better, or like what are we thinking? Need more time to process. Okay, okay, excellent. Love it, love it. Thank you so much for your feedback, by the way. I know that these are like small moments of feedback, but like as an instructor, especially because I don't have you right in front of me, it's really, really helpful to know sort of where you are, okay? All right, so let's do this. I'm gonna stop sharing here. Going to, all right, so we said more examples would be helpful. So let's take a look at example number 2. Okay, so I'll give you a moment to take a look at the 2 equations and think about what information you know about the shape of those graphs. Okay, and if you'd like, you can start plotting them as well. All right, so take a moment, unpack what you know in example number 2. Okay. So hopefully the start of your thinking looked something kind of like this, that if we can isolate y, that we can actually figure out what the shape looks like maybe a little bit better, right? And so in this situation, it looks like our pink equation is again a line. But this time our slope is 3/1 and our y-intercept is 2. Okay, so if we were to go ahead and plot that, we could start at 2 on the y-axis, and then we'll go up 3/1, up 3/1, and then we could go in the other direction, down 3/1, down 3/1, down 3/1, one more. Okay. And like before, we're able to connect these. And because we're looking at the picture, we want to make sure that we can extend the line across the whole graph to make sure we catch any intersection point. Yeah, so the slope comes from, the slope comes from this number, the coefficient in front of x, okay? Well, so we know that slope is like rise over run. So I sometimes like to make the slope into a fraction so that I can see what the rise is and I can see what the run is. You don't have to write the 1, but sometimes people forget and they think the slope is 3. They just keep counting up 3 and they never go over any, you know? Okay. All right. The orange curve looks like it's a parabola, okay? Does this parabola move side to side or up and down? Right. Does this parabola move side to side or up and down any? Okay. So when we think about whether it's going to move at all, we need to have like an x minus a number, or we need like a plus sign at the end. And in this case, we don't really have either of those, okay? And so this is almost the case where I know we didn't practice this one a lot, but Brian is correct. It does get stretched. This is a vertical stretch of 2, okay? Meaning that we're going to take all the y values. Y values are twice as big as a regular parabola, okay? And if you're not really sure what that looks like, then we can just kind of plug in points, right? So let's plug in 0 for x. If we plug in 0 for x, we're going to get a 0 for the y, right? And when we plug in 1 for x, we're going to get 2 out for y. So normally with a parabola, that first point is like 1 and then 1. But this time it's 1 and then 2, okay? What if I plug in 2 for the x? What value will I get for the y? Yeah, we're gonna get 8. So 2 and, whoa, 8, perfect. Well, looks like one of our solutions. Okay, and then if we use the idea of symmetry, we can plot the other point. So this point has a symmetrical point on the other side. And then this one at 2, 8 is also at negative 2, 8. And now when we connect these, oops, we can see that we have one intersection that should be at 2, 8. And we should have another intersection at, ooh, well, that's not a whole number. So this is one of the limitations of graphing, right? You can sketch it out all you want. You know there's two answers, but sometimes if it's not right at a lattice point, you might not know what the value of it is, okay? So we can see from here we have two intersections. We know one value. We could kind of guess the other one, but let's move to our algebraic work to try and figure out exactly what that other point is, okay? And so when I think back to example number 1, I said, I know that y equals y, and the pink y equals the orange y. And then I basically substituted both sides so that I had a situation where the pink equation equaled the orange equation. So we're gonna follow that same pattern right now and kind of see what happens. So we know y equals y. And by y equals y, I mean the pink one equals the orange one. And so in place of the pink y, what can I write? Yeah, I can replace that with 3x plus 2. Now similarly, for the orange y, I can replace that with 2x squared. Okay. Now we have our equation. 3x plus 2 equals 2x squared. And we're going to think about what we did last time. Last time, Thea said, let's move all the x's to one side. And I loved that idea. And then Eric made it even better. And he was like, well, let's just move everything to one side because we see the squared, right? Well, I see a squared. I see 2x squared. So in my brain, I'm automatically thinking, move all this stuff to the other side, set it equal to 0. So 0 equals 2x squared plus 3x plus 2. Okay. Now, this is a time when we do need to remember how to factor, right? So that factoring extra credit wasn't really like, oh, you're only going to need it for this test, so let's do it then. But that could be something that you kind of keep going back to help yourselves remember how to factor, okay? So let's kind of do this process of the factoring. And let's do it in blue. So if we think about the factoring by area, we put the b value on the top and we put a times c on the bottom. Right? So 3 is our b value, a times c is on the bottom, 4. Now I need to find a pair of numbers that multiply to make 4. Okay, so times to make 4, but add to make 3. Is that possible? Ah, good catch, good catch. So this is something I've actually seen on a few people's papers where they're just working so fast that they're like, yeah, just move it to the other side. And I know you need to switch the signs, but we really want to make sure we catch that for ourselves, right? So let me just change those to a minus and a minus, right? Because I move them to the other side, so it's a negative 3x and a negative 2. Okay, well, how does that change the x situation? I need a -4, so I need numbers that multiply to make -4, but also add or subtract to make -3. Right, let's see. If I have -4 plus 1, -4 times +1 is -4. Okay, that works out. And -4 plus 1 gives you -3. Good, that works out too. Okay, so we've got our pair, -4 and +1. Then we move into our area model. Okay. How do we start to fill out this area model? Anybody remember? Well, usually I go back to the equation. I pull the very first term and I put that in here. Top left-hand box. Yeah, and then that -4 and the 1 do go somewhere in the box, but let's think about where they go. So they go in the top right and the bottom left. Now I already wrote these in, but we want to make sure we understand those numbers represent the coefficients of the linear term. So like it's not just a -4, it's a -4x. And it's not just a +1, but it's a +1x. Okay. Now, the last box is actually your built-in check, right? So if this number at the end matches with all the rest of your work, then you know you factored correctly. And I think so often in math, we're like, oh, I mean, I did the problem. I don't know how to check it other than I looked over my work again. So I guess I'll just hope that it's either right or wrong. But when we look at this particular model, what I like about it is that we have a way to know whether we factored correctly or not. And so we're going to save writing in the answer in that bottom right-hand box until we found the outside part, okay? All right, so in order to make 2x squared, I could do this. Like I need a 2x and I need an x, right? And if I put an x on this side, that means this side is also x. So x times something is -4x. I could put a -4 up here. That would work. But if this side is 2x, this side is also 2x. Now 2x times what gives you a +1x? Yeah, we could do +1/2, okay? But generally, we try and keep our numbers whole numbers if we can, right? So if I wanted to think, is there a whole number that I can multiply 2 by to get 1? The answer would be like, no way. So all that means is you might want to go back and switch the initial order of your 2x and your x. So let's put the x up here and let's put the 2x on the side. Now that does mean you need to double check all the other numbers. You can't just switch those two and keep the number you had the first time, okay? So 2x times -2 will give me -4x, that works. And then x times a +1 will give me +1x. All right, so this is the magical moment. How do we know if we're correct or not? 1, which is this side, times -2, which is this side, gives me -2. And if that number matches your last number here, then you factored correctly. Okay? All right. So all of that in the middle of a problem, right? This wasn't even just a problem by itself. It's in the middle of another problem. And I don't want you to get to this kind of problem and be like, I mean, I understand how to do it, but I still don't know how to factor, right? I want us to be prepared for all these kinds. Because guess what? By the time we get to the end of Calc 1, this work is actually going to be inside of another problem. So we're going to have to graph some things, find out where they're equal, and then use that to solve the problem with calculus. Okay? So our factors, 2x plus 1, x minus 2. And you could have done this by grouping as well. That is absolutely fine. That means we have 2x plus 1 equals 0, x minus 2 equals 0. So we get x equals -1/2 and x equals 2. X equals 2 is good because that was 2. X equals -1/2 is actually also good because if we zoom into this graph, I bet we could sort of have guessed that that x value was going to be a 1/2 or -1/2. Excuse me. Okay. Remember, we want to give super clear directions. We want to make sure that we have the y values for those as well. And so we can plug the x back into any equation, the pink one, the orange one, it doesn't matter. If we plug this into the 3 times x plus 2, we'll get 8, which is good because 8 is the y value of that point. All right. And then we do the same thing with that -1/2 for x, and so I get 3 times -1/2 plus 2 is -3/2 plus 2, which is a +1/2. And that's really good because this y value is a +1/2. And that corresponds with the x value of -1/2. Okay. All right. So how are we feeling after this second example here? Good. A little bit better. Somehow a little less good. Okay. That happens. That happens. All right. Okay. Well, let's take a look at what else we have. Okay. So let's take a look at example number 3. Okay. So we've got two equations again. We've got this one and we've got this one, right? So take a moment, think about what shapes we have here based off of what we know about equations, right? We know a lot about equations and what the equation's actually telling us about the shape. Oh, I love it. Isis, which one is the circle?
The first equation.
The first equation, yes. Okay, so this one is a circle. And when we think about circles, the important features of a circle are the center and the radius, right? We don't need to worry about the foci or the vertices. We just need to know where's the center and how far out do we go in that direction. And so from here, I bet we can tell that the center is 0, 0, right? Because I don't have any like x minus 2 or y plus 2, right? I don't even need to complete the square. It's already done for me. So we have a center at 0, 0. What is our radius
Is that the square root of 5?
here? Oh, that is the most perfect answer. It is 100% the square root of 5, okay? Now, the reason why I chose this question is because sometimes we're like, I think I take the square root of 5, but we're so used to that number being a really nice square root that when we get a case where we have a square root of 5, we're like, I don't know, square roots are weird. Maybe I'm wrong. Maybe it's just 5, okay? But you're not wrong. It is the square root of 5. It is a quote unquote weird number. But if we punch that into the calculator, we'll get it's about 2 point, let's call it 2, okay? So to the best of our ability, let's kind of sketch out this graph, okay? So if we have 0, 0 is our center, and we go out like 2.2, 2.2, 2.2, 2.2, right? And we think about connecting all of those. Hey, that's not bad for a Wednesday morning, right? So we've got our circle here. Now let's take a look at the orange equation. What do we know about this orange equation? It's a linear function. I love it. It is a line. All right. What do we have for the, okay, all right, we've got a slope of 3/1 or 3. If the 1 bothers you, you don't have to write it down. And a y-intercept of -5. Good, good. Okay, so I'm going to go down to -5. And then I'm going to count up 3/1, up 3/1, up 3/1. And I'm going to connect those points. Well, close enough. And so we can see from here that our line goes through our circle 1, 2 times. And this is one of the sort of added benefits of like the technology of, oh, I could draw a perfect circle, right? When I do this lesson on the board, it is not a perfect circle. Sometimes it looks like a half-eaten donut, like it's not good, right? But in this case, we're gonna use this technology and say, all right, it's given us the exact value, right? But when you do these problems on your own, especially if you're, freehanding this, you're just trying to sketch it, what's important is you know how many times it crosses, but you might not be able to get an exact value if your graph isn't super accurate. But the graph here is really kind of like review for our final. Like, I want you to know how to graph these shapes. Think about what we've learned the entire semester. But in some cases, it can actually be really helpful to get the exact value, okay? But either way, what we really want to do is be able to confirm this algebraically. All right, so let's take a look at these two equations. We've used a lot of like solve for y and set them both equal to each other. Oh, what did you say? Estimate the coordinates. Yeah, if you're sketching these out, just estimate or circle them. And once you solve them algebraically, go back and write the coordinates in, okay? So it's more about, do we see that connection between those two rather than can we draw a very perfect circle, okay? Cool. All right, so what are our thoughts here in looking at the pink equation and the orange equation? What methods have we kind of talked about this semester that might be useful for us here? Substitution, tell us a little bit more. Like, what are we substituting? Since y is equal to something, yeah. So like in this equation, you have y equals 3x minus 5. Perfect. We can take that and we're going to plug it in everywhere we see a y. Okay? All right. So let's do that. So instead of x squared plus y squared equals 5, we have x squared plus 3x minus 5 squared equals 5. Okay. All right. What should we do from here, or what could we do from here? Yeah, we could FOIL that out for sure. So we get, let's see, 3x times 3x is 9x squared minus 30x plus 25 equals 5. Okay. So FOIL. All right. What do we want to do from here? Combine like terms, move the 5 to the left and factor. I couldn't have said it better myself. All right, so 10x squared minus 30x plus 20 equals 0. Okay. What can we do from here? I love that. Factor out that 10, divide by 10, but yeah, exactly. We are looking for getting rid of that greatest common factor, right? So we have x squared minus 3x plus 2. Well, gosh, that looks so much better to work with than the other number, right? And now, pretty sure this is factorable. And I think we get x minus 2 times x minus 1 equals 0. All right. This is looking good because I think those x values are going to match with the x values from our picture. X minus 2 equals 0, x minus 1 equals 0. And x equals 2, x equals 1. All right, let's see. Yeah, this is about 1 comma something. This is 2 comma something. This is good. This is good. Things are matching, right? So 2 and 1. And we've said earlier, we can find the y value by plugging in any x value we have into whichever equation, right? And before, I think it didn't really matter. It was pretty straightforward either way. But I think in this case, it might be wise to plug 2 and 1 into the line equation, the orange one, right? Just so I don't have to like square anything and then square root some things, right? I want to keep it simpler for myself. So y equals 3 times 2 minus 5, or y equals 1. And that's a 1 value, so that's good. This 1 is that 1. And then y equals 3 times 1 minus 5. That is 3 minus 5 is -2. -2 is good because I bet that value, if we look at our graph, is -2. Cool. All right, so we've set up our equations. It's not exactly step by step like the other ones we did, but I think what you folks have been really good about doing is trying to almost zoom out a little bit and see the bigger picture. And that's really important, okay? And you're willing to share your thoughts on why you're choosing to do something that you are. And that is part of this process, right? What we're doing here is really learning how to make decisions. Like, how do we know that we should substitute here? How do we know that we should FOIL? How do we know that we should factor out the greatest common factor, right? And the truth of it is sometimes you should and sometimes you shouldn't, but the more practice we do, the more we can kind of see, oh, okay, I get where this came from, right? All right, so 3 examples in, how we feeling. Things getting worse, things getting better, things about the same. Oh, good. I'm glad it's getting better. I know it's always a little scary when you're like, I don't think it's getting better yet. I don't know. Trig is, if you are a visual kind of learner, I think trig is actually pretty cool. Lots and lots of applications for sure. Okay. So let's do this. Let's take a look at example 5, okay? I love how you're looking ahead. Pretty sure the circle and ellipse are next, so maybe not better. Okay, well, let's try it, right? Let's try number 5. So let's go with our pink equation, our orange equation, and I'll give you a moment to figure out what those shapes look like, all right? So what do those shapes look like? And what features might be important about those? Yeah, I think that's a fair statement, Eric. I think that it's not necessarily new information, but it's combining a lot of things that we've learned. So if you're the kind of student who like actively seeks out all the connections as you're learning material, then I think this is not really that new, right? But I think some people, it's like, well, I'm learning this one thing, and then the next day I learn this other thing, but they're totally not connected, right? I think that's how some of us kind of feel. But the reality is there are usually a lot of connections between what we're doing. Yes, we've got a circle, we've got an ellipse, perfect. All right, so with our circle and with our ellipse, what do we know about them? Like, where are their centers? Can we sketch a quick picture of them? What do we know? Yeah, circles and the ellipse are both centered at the origin, okay? So don't be mad at me. I definitely made you do a lot of like work around completing the square, and you are gonna use that. You are gonna use that, but sometimes the equations are fairly straightforward. And I'll tell you, I was sitting in a Calc 3 class the other day, and they had equations that kind of look like this. And the teacher was like, well, what shape is this? And there were some people who didn't know. They did not know that that pink equation was a circle. And there were some people who didn't know that that orange equation was an ellipse. And that was, it's possible that maybe they forgot, but for some of them, it just didn't even ever seem familiar. They were like, I don't know, I don't think I've seen this before. Okay, so if you can look at these equations right now and say, I know that pink one is a circle and I know that orange one is an ellipse, that's important information to hold on to. Okay, it'll definitely make things easier when you start to layer on more pieces. So let's take a look at this one. We've got a circle. The center is at 0, 0, and our radius in this case, I think we will all correctly state that it's not 26, but it is the square root of 26, right? And if we put that into the calculator, we'll get about 5.1. Right, so let's go ahead and sketch this first. We know we have a radius of about 5.1. See, this is more like what usually happens when I'm drawing these on the board. Okay, close enough, close enough. Okay, well, we've got our circle. What do we need to do to the orange equation before we can actually sketch a graph of it? Square the 25. Ah, okay. Why are we squaring the 25? Ah, okay. Factor out the 3 and the 5. Okay, so this is where I was giving us questions that were like way more complicated than this, right? And so our goal was we had to complete the square so that we could get like a number times x minus a number squared. Like we were trying to create that squared. But if you look at what we have here, we actually already have the squared. Okay, we already have the squared. And so one of the things that I've been really picky on for this very reason is I want us to not just work with the left-hand side, but I want us to understand what it has to equal. So when we look at equations of ellipses and hyperbolas, that right-hand side has to equal 1. Remember, that's sort of the last step. And a lot of us were sort of dividing everything away on the left side, but then we would never write the equals 1. And I want us to write that as a reminder that in order for us to pull the important information from the equation, we have to make sure it equals So in this case, this ellipse is so much simpler than everything we've seen because the center is at the origin and it's already completed the square for us. The only thing we need to do is divide by that 100, okay? So if we're dividing by the 100, we're gonna get x squared, 3x squared over 100 plus 25y squared over 100. And if we simplify, we'll get x squared over 100 over 3 plus y squared over 4 equals 1. Okay. Now, I think the one set of points we could graph pretty well are these ones, right? From the center, we're going to go up and down how many units? 2, very nice. So 1, 2, 1, 2. So it seems like this is going to be an Ernie ellipse. It's going to be a little bit wider, right? Now this number, not so nice, but let's use our calculator to help us out. So we're going to have 100 over 3, and we want to take the square root of that number to know how far we're going to go side to side. And when we type that into the calculator, we get about 5.8. Okay. So 5.8, and about 5.8. And then if I connect everything, which planet has the belt again? Saturn? It looks like we have a Saturn situation, right? This is not an attractive diagram, my apologies. But we can see that we have this pink circle, we can have this orange ellipse, and they're gonna intersect 1, 2, 3, 4 times, okay? Now, I think even though my graph is not super, super accurate, I bet that I'm gonna have 5, comma 1 here. This one down here looks to be 5, comma negative 1. Yeah. And then on the other side, this looks to be negative 5, comma 1 and negative 5, comma negative 1. So at the end, we should get 4 solutions, right? And I think it was Ethan earlier who said, yeah, the degrees here maybe make a difference. Now, if we think about this, that is actually accurate, okay? So you can say that a circle, so a circle crosses a line at most how many times? 2, okay? And an ellipse crosses a line at most how many times? 2. All right. So if you think about combining those, there's no way you can get that they cross 5 times, okay? So if we almost scroll back up real quick to this chart with the 5 solutions, it is not possible to have a circle and an ellipse cross 5 times, okay? But Ethan, you brought up some really great ideas. Like if we're looking at a 3-dimensional space, then the number of intersections goes up by a lot. And so we're talking about a flat circle and a flat ellipse. But when you get to Calc 3, you'll talk about spheres and 3-dimensional ellipses and things like that, okay? So it was a trick, but it was also, I think, a really important thought process about like, how do we know for sure that things are or are not gonna work, okay? All right, let's go back down to number 5. Okay, so we've solved this graphically. We've established there are 4 solutions, but what we need to do now is confirm these 4 solutions using algebra. So let me give you a moment to take a look at the pink equation and the orange equation. What strategy might we want to try? What seems like it might work? We could set them both equal to 1. Okay. Plug one of the x coordinates into one of the equations. Elimination. Okay. All right, so let's kind of start with the first idea. So with the first idea of setting them both equal to 1, this one would be x squared over 26 plus y squared over 26 equals 1. And then I'd have this equation equals this equation. I think that's definitely possible, but that's a lot of fractions I don't really want to deal with right now. Okay, so certainly possible. Plug one of the x coordinates into one of the equations. Okay, so remember, we don't really know that these x coordinates are where they are yet, so we can't really use those. But if I wanted to like take this equation, x squared plus y squared equals 26, what does x equal? Right, if we have x squared plus y squared equals 26, how do we isolate x? Okay, so we're going to subtract that y squared, and then we'll take the square root. Okay, so square root of 26 minus y squared. So then by this idea, we would have to take 26 minus y, and we'd have to plug that in everywhere we see, whoops, not the y. Plug that in everywhere we see the x. I think that's actually not a bad idea, right? I think that the square root might be a little scary at first, but you're taking a square root and you're squaring it. So what you might get is 26 minus y squared plus 25y squared equals 100. I think that one feels fairly familiar. Let's see what happens with this, okay? But I do want to come back and talk about this elimination idea, because I actually think that one is perhaps the most efficient in this case, okay? All right, so if we distribute a little bit here, we've got 3 times 26 is going to give us 78 minus 3y squared plus 25y squared equals 100. Okay, so 25 minus 3, this will give us 22y squared. And when I subtract that 78 to the other side, I get 22. Now, y squared equals 1. What does y equal? Okay. So I appreciate how thorough you are in your response, plus or minus the square root of 1, right? So many people get to this point and they're like, y equals 1, done. But what happens? Let's see. If they only say y equals 1, let's try and find the x that goes with it, okay? I'm going to use the pink equation because I think it's a little bit easier. But then x squared plus 1 equals 26. X squared equals 25. And if this person made a mistake for the y equals 1, what do you think their answer is going to be for x? Like, what would they say x is equal to? They would say 5. And they'd call it a day. They said, I found my intersection, 5, 1. And you all would be like, well, here's your 5. Here's your 1. But overall, that person only got 25% of the solution. They only got one solution and there are 4. So that's kind of a lot that they didn't get, okay? This is why it's so, so important when we take that square root to remember we have to do the plus or minus. We have to consider that it could be the positive value that we squared, or it could be the negative value that we squared, okay? So let's be better than this person. Let's go back. Let's change our answer for y to be plus or minus 1, okay? Now, what is, I think, a better idea than just plugging in y one time is now that you have 2 y's, you plug in y equals 1, you plug in y equals negative 1, okay? And that will give you x squared plus 1 equals 26, or x squared equals 25, or x equals, be better than that person, plus or minus 5. Now, what happens when we do this with the second y value? X squared plus negative 1 squared equals 26. Same thing, x squared equals 25, or x equals plus or minus 5. Okay? So what this sort of tree-looking diagram tells us is that you can have 5, 1 as one solution, and 5, negative 1. Okay, because we keep this y value for both of those. Whoops. That's not what I meant to write. Negative 5, 1. We keep those that one y value for both of the x values. And we find there are 2 x values there which match with negative 5, 1. Oops. Okay. So these 2 correspond to this top one and to this left-hand side one. Now, how do we get the other set of points? Well, we take our answers from the right-hand branch and we get 5, negative 1 and negative 5, negative 1. And these 2 right here should correspond to this point and this point. Okay. So if you wonder why folks like mathematicians are like, oh, who cares about a plus minus sign? You just forgot one of them. When you layer it into a problem like this, you didn't just forget one solution, you forgot 3. Okay. And so that's why it's really important that we really make sure that we understand what it is that we're doing. Like when we see these complicated equations, all it's really saying is how many times does this circle cross this ellipse? That's all. Okay. All right, so it's about 213 right now. Do you want us to use a specific method or can we use any? Oh, right, the elimination. I did want to talk about that. I thought that was actually quite clever. Let me put this down here. Yep. Okay. What did we have? X squared plus y squared equals 26. And 3x squared plus 25y squared equals 100. So when you said elimination, what did you want to eliminate, or what did you need to do to eliminate something? Multiply by -3. I love this. Times -3. That's kind of long. So -3x squared minus 3y squared equals -78. Well, these numbers look familiar. 22y squared equals 22y, and then it's exactly the same as what we did before, right? So if you like elimination, like, you know, I'm already biased, but if you also enjoy elimination, this is a great way to get rid of one of the variables, right? If you're still feeling more secure with substitution, then I think there's nothing wrong with this other method either, okay? Yeah, anytime you have elimination, as long as all the letters match up together, okay? So let me move back down to the other screen and show you what I mean. This equation, I think we call this one the pink one, okay, has the form, well, something squared plus something else squared equals a number, right? And if we look at this orange one, it also looks like this. Something squared plus something else squared equals a number. So elimination actually only works when the forms are the same. So that's why we didn't use elimination with the linear and a circle, or the line and a parabola, because they weren't the same form. But if they're the same form, then you can use elimination, okay? So it probably is actually good to understand elimination as well as substitution. Right, Christina. So if one is squared and then the other one's not, so if I had something that was like something squared plus something equals a number, what you could do, you could maybe eliminate this and this, but then you cannot combine this one and this one because one is like a y squared and the other one's just a y. Okay. The other thing is you want to make sure things are lined up in the right order. So if this one is an x squared and a y squared, you want to make sure the orange one is also like the x squared first, the y squared second equals the number. Like everything is in the same spot, then you can use elimination. Okay, cool. All right, well, we've got about 20 minutes left in class. So I'm thinking. Let's do this. We're going to take a look at question number 6, okay? Because this is, I think, as we can kind of tell, similar to example 5, right? We see some x squares, we see some y squares. We've learned some different techniques. So what I'd like you folks to do, and I'm going to send you to some breakout rooms, is I'd like you to focus on solving these algebraically, right? That's the new skill here. So focus on solving it algebraically. If you and your group have time, then go ahead and get some graphs of these functions, okay? But the priority here is to solve them algebraically, all right? So example number 6, we'll give you about 10 minutes or so, see how that goes. If you finish this early in your groups, you're welcome to try any of the other examples in here. Whatever your group as a whole might want to focus on is fine. And then we'll come back together before we end class and then be on our merry way. Okay? Are there any clarifying questions before I send you off? All right. Yeah, it is actually going to be classwork 14, okay? So I'm going to ask folks to make sure they write down their own work for number 6, all right? And the part that I want you to send in is just the algebra part, okay? All right, folks, so let me send you off into your rooms. You know you can ask for help if you need any help by getting to that help button. And I'll see you in a little bit.